Hello everyone, welcome back to Introduction to Semiconductor Devices. In the previous video, we spoke about the short channel effects. We discussed how the reduction of channel length will influence the current characteristics of a MOSFET. And these are very, very important because I think about in 2000 or so, we have entered into the short channel regime. And now most of the MOSFETs are actually short channel MOSFETs, and it is important to understand them in detail. Okay. So now today, this video, the emphasis will be to understand the impact of shorter channel length on the VT of a MOSFET. So if you look at the derivation for VT that we have done, you might recall that VT had few components. We did this for the case of an ideal MOS cap, and that's exactly valid to the MOSFETs as well. Okay, so you have the flat band voltage, and then there is a minus QD by Cox term plus, for the case of VT, you will have 2 phi f, which is a surface potential, right? So this part is a surface potential, essentially the potential drop in the semiconductor, right? And this is my drop across the oxide, the potential drop across the oxide, okay? And then of course flat band to account for the differences in the work function or the interface charges and so on, right? So this is the definition of VT that we have studied. So if you look at this expression, do you think that there is any dependence of the channel length on the VT? Okay, to analyze that, what we will need to do is, let's just look at the structure of a MOSFET. Okay, so you have the source and the drain, source, drain, and then there is an oxide, and then there is a gate. So if you look at it from the top to gate to the substrate, it's simply a MOS cap, right? And there are going to be, this is P channel, let's say, P type substrate, so N channel device. So this is N plus and this is N plus. So in such a scenario, you will have a depletion region under the gate. Let's say the VG is positive here, okay? VG is greater than 0, okay? So there is going to be this depletion region under the gate, and also some depletion region around the source and the drain junctions, right? Because those are also PN junctions. Now, if you think about it, if you just look at it only from the top to bottom, okay, should there be any effect of the channel length on the VT? Well, no, right? Because we are not really considering the, when we derived this expression here on the top, we did not consider the effect of channel at all, right? We didn't even introduce channel at that point of time. We just simply took a MOS capacitor. So now how does the channel length influence the VT? To understand that, we need to look at what is the channel length here. The channel length is essentially the distance between the source and the drain, isn't it? So now, what is VT? VT is essentially the gate voltage required to first deplete the substrate and then create inversion charges, right? So it has to support the depletion charge, which is appearing in the VT expression as this 2 phi f, right? So now, when you have a long channel device, okay, and you must remember that there is this part of the junction which is supported by the source. This part, this depletion region is supported near the edges, right? This is supported by the source and the drain. They are also reverse biased, correct? At best, in this case of source is at ground and bulk is at ground, so there should be some built-in depletion with something, right? And then in the case of a drain junction, in a typical NMOS, we might have actually VD greater than 0. So this drain junction is reverse biased. Okay, drain junction is reverse biased, right? Because we are applying positive voltage to the N-type device, so it's reverse biased. So what's happening is the gate is supposed to support the entire depletion charge. Okay, always, in a MOS capacitor device, you have a positive charge on the gate, let's say. So the negative charge has to come from the substrate. So now what happens is you have 3 contributions. So positive charge on gate, right? In the MOS cap case, it has to be entirely in the substrate, we said. So depletion charge plus the inversion charge. right? That's what we said. So this is on one side of the equation. This should be balanced by what? So you have the depletion charge, QD of the bulk, okay, QD bulk, and then there is depletion charge in the source and the drain junctions, right? So QD source, okay, I should actually write a plus here because all of that should be added up, okay, plus QD drain. So at the drain junction and at the source junction also there is some charge which is being supported by the potential on the source and the drain, not the gate, right? So this entire positive charge on the gate should be balanced by these three charges. Okay, let's assume that inversion is not so significant right now. Okay, so this charge, gate, this balancing charge, negative charge, has to be shared by these three terminals: bulk, drain, and source. Okay, so because of that, the amount of gate voltage necessary to create inversion is reduced because part of the depletion charge is supported by the source and the drain. Okay, so because of charge sharing, due to charge sharing, VG, right, needs to support smaller depletion charge. And this implies that VT is reduced. Okay. Now, well, if your channel is very long, then the amount of depletion charge at the source and the drain junctions is going to be very, very small, insignificant. Okay. But as you go to smaller and smaller dimensions, if you say that this is, let's call it XD, the junction depth here, junction XS. So if XD and XS are, let's say, if XD, XX are comparable to L, then VT will be strongly affected. Okay. And that's what we see here. I mean, in the graph here, we are showing different VTs for different channel lengths. So x-axis is a channel length. As you reduce the channel length, what happens? So y-axis is a VT. So let's take the first case of, drain bias is very small, okay, 0.125, 125 millivolts. So let's assume that it's in the linear regime, okay. So what happens? Well, initially when the channel length is long, nothing much happens if you reduce it. But once you hit the short channel regime, when your depletion width at the source and the drain junctions is comparable to the channel length, then the VT starts reducing. And this is the trend you see. As you go to smaller and smaller channel length, the VT is reducing because the gate is supporting lesser amount of depletion charge. So the VT will reduce. Now what happens if I apply a drain voltage, positive drain voltage? The second case is here you have a positive drain voltage of, let's say, 4 volts. Okay. So we know that this, okay, I'm sorry, it should be pen. Okay. So drain bias causes depletion width at the drain junction, right? Let's say XD drain, XD we called it, right? Causes XD to increase. That means VT has to be even lower, right? So that's why we see that implies VT lower, right? That's why when you compare with no drain bias, which is the first situation, sorry, a small drain bias, which is only 0.125, and compare that to a reasonably large drain bias of 4 volts. If you introduce that, essentially your depletion width on the drain side is going to be much larger, and so that impact is going to be strongly felt. Okay, so this is how the VT will fall faster. And what if I apply a bulk potential? In this case, bulk is P-type, right? And I'm applying a VBS of 1.25 volts. So I'm positively biasing. So forward biasing the drain bulk junction. If I forward bias the drain bulk junction, I'll reduce my depletion width. So the gate has to, we have to apply greater voltage at the gate to support the same amount of depletion charge. That's why you expect that, the VT is higher initially in the case of positive bulk. But then if you go to smaller and smaller channel lengths, you're actually making it easier. The barrier is lowering on the source side. So you're actually making it easier for the current to flow. That's why VT falls. But still it's going to be compared to VBS of 0, it is going to be higher. Okay. So these are the trends. So when you look at it for the first time, I'm sure it can be slightly confusing. So my effort here is not really to make sure that you understand all the details. I want you to understand what are the factors that you need to consider. Okay. So my strong suggestion is you stop the video here, just look at the graph and try to explain it in your own words. That will clarify your thoughts. Okay. If you feel that somewhere you're actually missing the link, then you can go back and revisit the video and again do it one more time. Okay. So you should not try to remember this thing. There is no way that you'll be able to remember. I mean, you'll forget it eventually, right? So the better approach would be to try to analyze it for yourself and see what comes out. Okay. So based on the principles we have developed in the MOSFETs and even the PN junctions, I think the explanation should come forward. So whatever I have discussed just now will be helpful for you to analyze for yourself. Okay. If you still have any questions, of course, I'm available for a discussion. So we can do that. Okay. I'm just trying to tell you that as you go to more advanced technologies, things become more complicated. Okay. It's not the simple things that we learned. So we need to be aware of these things. And nowadays, nobody really, we have a lot of computer tools that will help us calculate all these things. So we don't do it with pen and paper anymore. Okay, all of this design is done using computer-aided tools, TCAD tools we call them, technology computer-aided design. Okay, so anyway, yeah. So I just want you to be introduced to what are the various factors that are at play. All right. Okay, this is a short channel effect. Now there's one more thing that we can do, which is narrow channel. Because you remember when we talked about a MOSFET, the top view of the MOSFET, right? We discussed it a couple of times, wherein we had this source and drain regions, and we said this is the gate on the top, if you look at it. So this is my source, this is my drain, this is my length of the channel, right? So length of channel is what plays a lot of important role. So we discussed it at length. So we always kept drawing the band diagrams along the source to the drain. But then another important feature is the width. If you increase the width of the transistor, then more current flows, right? But then if you're scaling down the width as well, right? Both length and width are being scaled. So what happens if you go to smaller and smaller widths? Okay. So here, the VT behavior is exactly opposite to the narrow, short channel. Okay. If you make a narrow channel, that is, you make it less wide, the VT increases rather than decrease like in the previous case. Why does that happen? Well, to understand that, you need to visualize the MOSFET a little bit. Okay. So I have shown some three-dimensional picture as well in the beginning of MOSFET discussion, so you can go back and look at it. So what happens is you take the cross section along the width, and this is how it looks. So you have the gate oxide here. This is gate oxide. And under the gate oxide, there should be a depletion region. If you apply a positive voltage right onto the gate, then you should deplete. This is my depletion region under the gate oxide. But it is never going to happen that it will be exactly under. There's going to be some penetration of the depletion region under the field oxide. So this region, right, which is supposed to be field oxide, means it is meant to isolate two different transistors so that they don't talk to each other, right? So, but when you apply gate voltage, some of the gate voltage, gate charge is going to be spent in balancing some depletion charge under the field oxide. There's going to be some spread under that, okay, because you're never going to have perfectly vertical lines. Well, if your width of the device is large, then this doesn't really matter. So let me call this, I think here, let me call it as excess, let me call it as excess depletion charge. Okay, QD, depletion charge, QD. Okay, this is excess depletion charge. So when your channel is wide, the fraction, okay, let me call it QD prime. Okay, the QD is basically the depletion charge under the oxide. Okay, QD is basically depletion charge under the oxide. So what is the total amount of charge that you have? You should have total QD, or total depletion charge. is going to be QD, which is under the gate, plus QD prime under one side of the transistor, and another side of the transistor, another QD prime. So these additional regions, right? This excess region that I called, I'm putting it in blue here, dark blue. So this is the additional QD that you have to support under the field oxide. So if you have width is large, then this QD prime is going to be very, very small, insignificant. So it doesn't matter much. But once you come to narrow channel devices, when your width reduces, you have this additional baggage that you have to support, additional depletion charge that has to be supported. Okay. So if VW reduces, QD prime is significant. And you have to support that as well. So QD prime is significant, implies gate has to be having a larger voltage so that you put a greater gate charge, and that will balance out this additional QD prime. Okay, so VT should increase. And this is exactly what you see here in the picture. And this is again taken from the textbook. But if you look at the textbook, they'll do a lot of derivations and try to convince you. But I would suggest you don't require to go into all the derivations here. You just need to understand the physical effects. Okay, that's enough for us. So this is channel width, and this is the voltage. So as you go to smaller and smaller widths, you see that the threshold voltage is increasing. Okay, and of course, there is an additional data point here, which is the substrate doping. If you increase your substrate doping, the VT increases. Okay, this also I think I leave it for you to analyze. It should happen. We have discussed this in some depth when we're talking about the MOSCAP CV. Okay, so yeah. Anyway, so this is the trend that is significant. So to summarize, there are two effects. One is on VT. One is let's call this length or width. Both I'll plot on the same graph. So if your length or width is large, I'll put it in black. If the length is large, VT is constant. But once you come to short channel, VT reduces. Okay. But you have a narrow channel. Okay. Initially, the width was large, VT is not changing much. But then if you come to narrow channel, VT increases. All right. So these are the two prominent effects that happen. So this is again just to tell you that the device design is complicated. I mean, it's not that simple, but our fundamentals that we learned in the beginning part of the course, right, in PN junctions and the MOSFETs, MOSCAP, will help you understand all these things. Okay. So these are two effects of short channels on a short and narrow channel on the VT. There is one last thing that I want to discuss briefly before I stop the discussion. That is what is called as drain-induced barrier lowering. Okay, so we saw the band diagram when there is no drain bias applied. So we have drawn band diagrams from the source through the channel into the drain. When there is no bias applied, we saw that there is a barrier created, and when you apply gate voltage, if I apply VG here, VG increases, this barrier, right? Barrier reduces. So current flows. This is the basic operation of a MOSFET, correct? That's why the current flows. After above a certain threshold, the barrier is completely removed. You have exponentially large current, right? That's how gate. It's just like a PN junction. When the barrier is reduced, you have exponentially increasing current. So one question to ask is, does the drain voltage have any influence on the barrier? Initially, if the channel length is long, if this channel length L is long, right? L is long, channel length is long, what will happen if I apply drain voltage? Let's say I'm applying drain voltage is positive, right, for NMOS devices. So what am I doing? So this was the Fermi level of an equilibrium, without drain bias, right? Drain bias, or I'll call it VDS equal to 0. But now I'm adding a drain voltage, right? I'm increasing the drain bias. And if I do that, I'm going to pull my Fermi level lower. Relative to the equilibrium case, this VDS is, this is causing the Fermi level to come down, right? EF is lowered. We have discussed this as well, right? When we are drawing the band diagrams. But And this is actually essentially your reverse biasing. If you are increasing the VDS, your drain junction uh, reverse bias is increasing, right? Reverse bias increases. That means the barrier increases, barrier height increases, right? But it doesn't really influence your current much, okay? Because current is dependent on two barriers. One is a source barrier, one is a drain barrier. The drain barrier is increasing, but that shouldn't affect your source barrier. So you still have the same similar current. But the moment you go to short channel devices, what happens? Well, this is basically a picture of the long channel case, okay? And then superposed on that is a short channel device. Okay, if you have a short channel device, what happens is, because you have to lower the Fermi level of the drain side, automatically the barrier is going to become it's going to become smaller. Okay, because this barrier is lowered due to drain bias. Remember, these barriers are energies, right? I mean, you're going to have some quadratic relations and things like that. It will not be steep, perfect junctions, right? It's going to have a certain field depending on the density, right? Charge density, background space charge, how it is. Depending on that, you can calculate these things. It's going to be some sort of a quadratic behavior, but then you're forcing this because you don't have sufficient voltage, sufficient distance for it to flatten out. So you're actually forcing the barrier to take a shape like this. So what does it mean? We are actually making it easier for the charges to flow across the channel, right? The source barrier is reduced, so the current should increase or VT should reduce, correct? So this is called as drain-induced barrier lowering. I mean, there is nothing very significantly complicated about it. It's simply if you understand the basic band diagrams, you would see this immediately. Okay. So how does that influence? So this is the last thing that I want to show about the short channel effects. If you have a long channel device, 10 micron long, and you measure the IDVG at two different drain bias of 50 millivolts and drain bias of 1.8 volts. We're simply changing the drain bias. And as we discussed, of course, when you turn on the MOSFET, there's going to be a stronger current. That is okay. That's what you see here. This increase in the current is expected, right? But in the off state, when you have these barriers, we don't expect the drain barrier to influence the current, okay? Because of which you see that off current here, off current is same for both VDS, okay? This is what you would expect in a long channel device. But the moment you go to a short channel device, which is 0.18 micron technology, 0.18 micron length, what should happen? Well, you have the lower VDS, IDVG, and then if you go to the higher VDS, because of the drain bias, the barrier is lowered, and because of which the VT has shifted. VT reduces due to drain induced, or I'll call it Dibble straight away, drain induced barrier lowering. So this is another feature that is noticed in the short channel devices. Okay. So as I told you before as well, my goal is to simply outline a few short channel effects that you need to be aware of if you are pursuing deeper into the study of electronic devices. Okay. This is not exhaustive. There are many, many more things. But of course, this you would do at a master's level. You don't need to do it at this point of time. Okay. You'll learn it at a greater detail so that you can understand the current technology. There are many, many things. Suppose, I mean, these sort of features are very useful when you're trying to understand VLSI design. Because if you look at VLSI design, there are computer-aided tools, CAD tools that will allow you to simulate various devices. For most of the engineers, I see that, design engineers, this is all black box. They simply don't understand what it is. But if you understand these basics, then all of these SPICE models and things like that make a lot of sense. So you can actually look into the SPICE models and understand what is happening and things like that. Okay, so it will give you a strong foundation for any VLSI design related courses that you take in the future. All right, so that's it. I would like to stop the discussion here. So this lecture essentially we focused on various short channel effects. What happens if you have the first video we have seen the current, how the current changes for short channel devices, and the second video we have seen how the threshold voltage changes. Okay, so these things are not very intuitive. You would not, I mean, I would not expect you to know it if you have not heard about it before. But once you have seen the lecture, I think it should sound intuitively correct. Okay, that's my goal. So I'll give you a few assignment questions which will help you reinforce these concepts. Please try to attempt them, and then if you have any questions, we can discuss them. All right. So with that, I would like to stop this lecture. I'll see you in the next lecture. Thank you so much. Have a great day. Bye.